Good evening. Hello, sir. Am I audible?
Yeah, audible.
One minute. Sir. Good evening. I welcome you all for the day 5, session 9 of 6 days online FDP titled Innovations in Additive Manufacturing for Green and Sustainable Future. Here we have expert Dr. R. Ravivarman sir from NIT Agartala. It is my immense pleasure to welcome Dr. R. Ravivarman sir. Welcome you, sir.
Thank you.
Dr. Ravi Varman sir received B.Tech Mechanical, M.Tech Product Design and Manufacturing, PhD Mechanical from Pondicherry University. He has more than 12 years of teaching experience. He has achieved many government fellowships and awards like University Gold Medalist, Inspire Fellow, DST Government Funded, etc. He has published more than 30 peer-reviewed articles and attended more than 15 international conferences. Also, he has published 5 books in the field of beer. Also, he is acting as editor in some international journals. At present, he is doing a government-funded project titled Autonomous Underwater Vehicles. Currently, he is working as assistant professor in the Department of Mechanical Engineering, National Institute of Technology, Agartala. Welcome you, sir.
Thank you. Thank you for the
Now I,
introduction.
now I
So,
request Dr. Ravi Verma, sir to start session 9.
ah, so I'll put my screen sharing on. My screen is visible,
Yes, sir. But it is not in full screen mode, sir.
not in full screen mode. Just a minute. No?
Yes, sir. Now it is full in full screen mode.
Okay. So, good evening, all. So, so I welcome you all for this ATAL sponsored online FTP program. So for the last 4 days, so you have been engaged in this program in the evening session on the topic additive manufacturing, right? So today's presentation will be on sustainable design for additive manufacturing. So myself, Dr. R. Ravivarman. So as sir has given the introduction, I am currently working in NIT Agartala as assistant professor. So briefly, the overview of the topics to be discussed today in this session. So the introduction and objective of this presentation. So what is the design fundamentals and its role in additive manufacturing? So the design workflow and digital process chain in additive manufacturing. Functional design replacements. So what we are going being carried out in the industrial practice in additive manufacturing. and sustainable practices that we are following in the design stages by maintaining a better efficiency with the materials, and the industry roadmap or the mentor role in sustainable additive manufacturing, and the government fundings towards this, and sustainable additive manufacturing implementations. So what the companies are doing, and few case studies under which we are working, then conclusion and the question and session. So moving to the session objective. So here we will be seeing about the design related things with respect to this additive manufacturing. So before covering to that, we will be discussing about what is the fundamental principles of additive manufacturing and how we apply this design procedure. So in additive manufacturing, DFMA techniques. So exploring its step-by-step procedure that we are using in the additive manufacturing design workflow, and evaluate real world case studies, how they have been used in the real world, how they have been efficiently transferring uh, from the conventional machining process to conventional manufacturing process to this new method, integrating this AM with new design factors. Okay, identifying the strategies to reduce material waste and improve sustainability, and integrate additive manufacturing with the design into academic curricula and research. What is the current state now? So, as you all seeing this topic for the last 4 days, so I'm just touching it and then going into the topic. So, additive manufacturing, as of know, that is the process of creating a three-dimensional part by adding material layer by layer. So, directly from a digital model. Okay. So here we the conventional process, what we do, we subtract materials, so like milling in the lathe operation or drilling, whereas in additive manufacturing, this material waste has been minimized. So with a less resource, we are trying to develop the same materials, which enables us to work in the complex geometries and supports the demand and decentralized production. So the major thing is will be helping us in quicker production states, and with reduced tooling cost and other things. Okay, so as a comparative thing between additive versus subtractive manufacturing, so here you see that in the process flow chart, the A and B. So we have a solid material. So we subtract the material according to our requirement and bring the required object. So the waste generated, whereas is lot, the amount or the percentage of waste generated is high in a subtractive manufacturing process. Whereas in additive manufacturing process, the materials waste generated is very less, because we are adding layers according to our requirement and the design shape. So here the very common example has been showed here, a coffee cup. So here the cup, you see that when you have to machine this, when the cup, you have to create the cavity here from the solid material. When we subtract from the solid material, the cavity has to be generated, and all the material will be as added as a waste. So which creates a lots of waste, so that the cycle is the cycle is incomplete, that lots of energy has been wasted to machine that. So the energy consumption is there, material waste is there. So this has to be reduced. So our objective, always the engineer objective, is we are working towards a better environment with newer process and technologies, correct? So the way here we see that all the process we make requires a special missions, so which generate these models from stage by stage. Okay, so the process of this additive manufacturing, so from the step by step procedure of this additive manufacturing, so first we will be creating the design. So how we are creating the design is very important, because you say that we can create a design, say same thing, we can make it as a solid model, and then we provide some ribs or extra provisions or support to that model, so that the when this file has to be given, or the CAD file has to be given as an input to that additive manufacturing process, so the which is given in the STL file format. So we have to make sure that the design what we are using, so which will be helping us in reducing the material by having a proper strength in the integrity of the materials. Because you see that when we try to create a solid material, we are not optimizely using the material, what will happen? So again we will be pushing that we are pushing to a scenario that we are wasting the materials, so that again we are building a solid materials which requires more amount of material to be substituted in, and that manufacturing process also takes a lot of time. So our design should be created in such a way that the design is a well proper design, so that we can able to reduce the machining time, cost, and the material usage, so that we support to the towards the sustainability goals. So, okay, and other factors like the uh, cost wise, and then the energy wise, we can also save time. So here in this process we see, once the CAD file is generated, after that we will be developing or converting it into the STL file format and then transfer to the machine. So in the third stage, whereas in the fourth stage, the machine setup. So we have uh, come towards very um, high profile machines which are more specific nowadays, with the different processes which can able to create this models with the more accuracies nowadays. So this has been evolved for the last 20 years or so. We can say that the evolution of this additive manufacturing is so good, so that we can able to see that all these processes are being getting more and more reliable nowadays. Okay, so after that, the mission setup, once we prepare to the mission setup, building the prototype, and then we are doing the part post processing operation, after which the component has been created, then we do the inspection of the parts and deliver the final good. So this is a very common example or a simple example which has been showed here, so that you can able to relate it with the things. So how this CAD model is being converted into a STL format. So here you see that all these are triangular shaped nodes. We can develop it, and you can see that the model has been sliced by layer, and it has been developed. Okay, so here is some small video of about how this additive manufacturing works. So here you can see that, so in this STL, a triangulated representation of the 3D model is created. So this model helps you. So the slice parameter, layer right, what is the density? After that, it is been printed. So what is that methodology we use for printing it? So we rely on that. So various materials we can use, like now we have metal additives, then this is being used for implants also. So we are using. So here you can see that this different operations, how this powder materials is being deposited. After that, this deposited materials is being printed by using some binders in it. So the after that, the platform is lowered, so that the stage by stage the product is being built up. So the major advantages here, we can see high productivity. The production is getting increased majorly by uh, reducing the material waste. Okay, and then saving the energy. So this picturized view of showing a gear, how it is being developed in uh, AM methodology, additive manufacturing methodology. So We have lots of types in that. So one such type is the material extrusion process. So the feedstock can be inexpensive, reduced one. Okay. So, so seeing this methodology, why this additive manufacturing is becoming important in day-to-day's manufacturing process, because they are more cost effective. So we have the flexibility in meeting the market demands. Nowadays, we can see that there is requirement of new products with lesser manufacturing methodologies. So we are trying to get the or retrieve the shapes, and we want to manufacture it more more reliable, and then which is having the um, better aesthetic look. Okay, so that way you see na, the like we can see that this additive manufacturing is coming into every field nowadays, from aerospace to our human bodies and implants. So we can able to develop a customized one which is with respect to specific to person. So where which have a better sustainability goal and waste reduction, which is more aligned towards the these climatic changes or the government schemes and other things. Okay, so we can able to create a on demand production and reduce the inventory cost over the material storage, and lightweight with better performance, with reduced risk in product development. So we see that newer products and with the newer functionalities has been generated in our recent days. Okay, so which all this factor makes this additive manufacturing more important in the day-to-day scenarios. So the key industries which use this additive manufacturing, you can see that from aerospace, from tool mold making, even in electronics, and then normal sports equipments. What we make, we say you are there. We have shown with the shoes. So there are we humans have different profiles of the legs, right? So accordingly, now they are making more personalized shoes. So you maybe one may be having that arch in the foot, one may be having a flat foot. So based on their requirement, so person to person, this has been changing. So we can this will can help to read, so that can scan your foot, and so that we can able to manufacture or produce a customized product in a low cost. That is very important. You see nowadays, the vehicle you take or any product you take, if you go for customization, it will be costing you more. But this we are making customized using additive manufacturing, so we can able to get it in a very easy process flow with less effort and less material waste and other, right? So the day to days like implants in textile fields, automotives, okay, then different sectors. So all these places we are trying to utilize this additive manufacturing, which has been growing largely. So the percentage of involvement of producing this additive manufacturing materials has been grown up drastically in the recent years. So why this additive manufacturing? So as we are aware that this is going to create a or this is creating a huge impact in the manufacturing process in nowadays. How design plays a major role in predicting the performance of this additive manufactured products. So in traditional manufacturing, you see, we must consider the tool assets, how we can able to utilize the tools which have been used in machining, so that the tool can travel into the machining pathways, or when you are doing a casting process, how the molding part lines has been differentiated, where we have to give it, whether the mold, what is the runner, riser, all the specifications we have to take into considerations. So here that then we have the limited usage of cutter tools. We cannot go for different materials. Then casting gates and die constraints. So we cannot able to produce a component as our own requirement. But that now, due to the design, due to this additive manufacturing, which allows us to develop complex internal structures like lattice structures, honeycomb structures internally, so that they provide a better strength, okay, enables good geometries, then customizing or customization of the material weight, okay. So then part consolidation, multiple parts, we no need to redesign again and again. But the major thing, how we are well deploying this additive design process. So in the how we are well deploying is, we have to use this design for additive manufacturing skills in a more better way before we go into this process actually. So first, the manage in a poor way, how it is the diagram here. These two diagrams explain you how this is. So the major thing is, you require to get a better feedback, so that the from the management what they are expecting. So what is to be added in your design. So better design for additive manufacturing. So full you have to create a better work order. So successful and unsuccessful part, you have to be in a position to segregate it properly. Feedbacks on that print which has been developed during the operations. After that, utilization of the report, and the capabilities or the recommendations that has to be supported into it has to be taken into consideration. So here are some of the examples. So what are the benefits because of this design wise when we made in through additive manufacturing? Some examples are given here. So this buckle, you can see that, which is being used in aircraft. So aircraft, we approximately we can take that in a normal uh, passenger aircraft, say there are about 180 seats. So obviously with the air hostess and the pilot, so around 190 seats, so 190 buckles will be there. So when you use a conventional process to develop this, so we create this steel buckle of 155-gram weight. So this has to be uh, when you go for a optimized design. So during, because of this additive manufacturing, when I want to create the buckle, uh, so which you can see that in the right side we have a optimize the design, where inside the material is being saved by not reducing in its strength. With no reduction of the strength, the material has been designed so that the buckle with less weight. So there is almost 55% of the reduction of the weight. So for a plane with the Airbus 380 with all economic seat of around 900 seats, so this is a weight reduction of 72.5 kgs approximately. So in a lifetime of this aeroplane, you take it about saves 3.3 million liters of fuel approx. So which is a huge energy consumption. So you can see that how a small product this has been come into the life using this additive manufacturing, how they are saving the material, saving the time, saving the fuel cost involved in it. So there are lots of benefits by using optimum, say same design, the same traditional design we can make and make it with the additive manufacturing process, but there is no use. So here you see that there are ribs provided in between the layers, so that we with better strength integrity you can able to develop a less weighted component, which saves a lots of money and carbon dioxide reduction to the surrounding and the environments, correct? So here there are some additional benefits also, like the complexities are very less. So this additive manufacturing enables the manufacturing of new geometric shapes that are not possible with the conventional methods. So the direct conventional methods you take, you have to take listen to the tool making cost. So how much I want to rely on making a tools. So additive manufacturing making it possible to design. So more here we have this um, cooling channels, so that cools the tools components better. Therefore, we get a reduced cycle time. So there is a graph showing the cost and the complexities, where you see that the additive manufacturing is cost-wise more effective and having a higher complexity. Whereas if you go with the same process in the conventional machining, so here you see that so the cost-wise it will be conventional machining. The cost-wise it is more when you increase the complexity of the clear. So the major benefits of this additive manufacturing for uh, customized medical products, so which is being used more long back in the dental implants. So here we see that also a large shares in dental crowns and the bridges markets, where the geometry is being scanned and then processed through a CAD CAM software. So for that we can able to create the exact requirement of the shape, thereby the market shares has been increasing in the fast production. So this also provides advantage with regard to the manufacturing time, geometry, fit, and the materials. Where the skull implants, a particular implant for a particular human, has to be created. So this additive manufacturing plays a vital role. So in future, so if we are planning for a future, now we have been provided with the normal printers, right, where how printers has been used. Like that we are in future we may be having a home 3D printer, where we you develop this our requirements on our need based. So accordingly we can able to uh, recycle the old material, so that we can improve input our personalized data, so that we can able to create it. Nowadays you can see that this cell phone covers also, you can see that personalized things they are printing it over it, so that this has been developed. Clear. So now we come into the design for additive manufacturing. So the design for additive manufacturing is very important to take into consideration before you are going to process or develop the product. So such as the topology optimization, lattice structuring, part consolidation to improve the function, reduce material usage, and minimize the supports during the process. So all this has to be applied during the design for that particular component produced through additive manufacturing. So the increased complexity does not equal increased cost. So that is one of the important thing. So you should get a benefit of considerable advantages over the traditional methods for design optimization. So when you are doing the design with a better optimized way, so your price or the cost to make this product is to be reduced. So that will be the objective towards which we will be working. So the total cost of production does not change significantly for larger volumes. So this is also one of the important factors. So when I make slight variations or some similar designs, cost approximately the same as making many identical parts. So it should create opportunities for mass customization and tooling. So when see in a conventional process, if I trying to make some changes minimally also, I should fully rely on the tools also. It's like the whatever the casting you see, the mold you create, or a die you manufacture. So you have to bring all the changes into it. So that is the major thing which plays the tool cost plays a major role when we are trying to bring these things into it. You can see that nowadays we see that more cars is models has been coming very quick time. So we can able to see that new cars are being coming into market with a very and more competitive. Whenever we get one model SUVs in one's brand, at the similar immediately they are trying to copy it and convert in the other brand as a competitor. The why? Because is all here in the some decades back, if you consider, so we want to bring some modifications. When you want to bring some modifications in the line, in the production unit, you want to think about the toolings. So nowadays, because of this advancement, so the tooling cost is also reduced, so that you can able to bring the variations. So any surface profiles I need to create, any look wise, aerodynamic wise, I want to improve the sys- the product. We are very easily developing it. Okay, so that is the impact of bringing this additive manufacturing into the uh, conventional process, or replacing the conventional process with additive manufacturing. So the impact of design for additive manufacturing in tooling and the production parts, rapid prototyping is high, and we have a lot of design freedom in that. Okay, so we have to follow some principles. So for this design for additive manufacturing, so there are 7 principles listed out here. So here you see that think additively. So we always should be thinking like adding the materials, not subtracting the materials. And we have to think about the design for orientation. So how contours are to be designed in by integrating the surface, the segments and the bond parts development, and adding adverse to the system, like making provisions for inserting some screws. That's so standard things we have to add into it. So minimize complications in the design. So critical surface treatment. Okay, so we'll be seeing one by one. So here table has been shown, which tells you the resource reduction and the quality enhancement with regard to the weight, cost, and the print time, the strength, aesthetic, and the functionality. So here you see that how these process are helping you to reduce the weight and the cost, the printing time and the touch time, that is the reduction time in the production, the enhancement in the strength, look enhancement, functionality enhancement. So the first step is think additively. So most manufacturing methods are subtractive, like the conventional ones. So here you see that there is a rib shown, which is having a solid uh, structure. Okay, but the requirement is they are being used for the purpose of holding the links. Okay, so the here you see that less materials used yield cost and time saving. So what we have to do, we have to reduce the materials in between the solid areas, so that we can able to provide some ribs or fillets, so that we reduce the stress concentration points, which also enable you to create a more safer component which doesn't fails, adding additional strength without adding the tooling cost. So you can able to see here how a better design when using through this design can be evolved. So stage by stage process is being showed, so that you can see that the here in the first portion you see that there is a steep contours which has been used with fillets, and similarly ribs has been added, so that you have the better strength integrity, and then reduced stress intensity factor also, right? So similarly we have another examples. We have this BMW badge placement, right? So here you see that in original design, you by thinking subtractive, that is creating a solid, after that subtracting, so we required a heavy bar for stock construction, so which requires 18 days to manufacture and assemble it. So and a significant assembly, multiple setup CNC at high internal cost, so unsatisfactory ergonomics, you can see that the comfort is not provided. Whereas when you have an improved design of this process by through additive manufacturing, you see that 28% of the original weight has been reduced by BMW by incorporating additive manufacturing through design only. Okay, so and the manufacture time has been reduced from 18 days to 1.5 days to manufacture and assemble it. So printed in one piece, so the hardware is inserted afterwards, so then single setup additive, so 69% of the original cost, and has better ergonomics to the person who is handling it. So this way, when the first step in the design for additive manufacturing is our concept of visualizing to create should be in the process of additive manufacturing only, not by subtractive way of conventional method of manufacturing, right? So the second process is the design for orientation. So in which way I need to orient it? So here we have a tensile specimen. You see that this tensile specimen we have kept in three direction, x, y and z direction. So we see that how this material has been built when placed in the z direction on its edge. So the building direction is x z axis, and when y direction, that is the flat building along the flat surface, and building along the upright. So when you apply the load for this additively manufactured material, you see that this is a layer by layer adding material. So for this z direction upright, when you apply the load along the normal load, when you're trying to apply the normal load, that is the tensile load, you can see that how this layering is being split up. So that binder strength is being broken, and then the material is failing. Whereas in the case of x and y directions, you can see that the specimen fails like a normal homogeneous structure. So here also there is a plot explaining you the tensile strength. Okay, tensile strength of this x and z components. So how it has been varied with respect to the strain at during breakage. Okay, for SLS made through SLS made materials. Okay, through the process of PA 112, right? So here you see that in which way I am going to create this slicing plays an important role. So how I am going to orient this design, so that this design, how this is being developed in the z direction, in which direction, upright direction I am going to consider it while considering the design for this AM parts. Okay, so another one example, here you see that there are two components which there are two pictures shown have the orientation in mind while designing a part to minimize the supports. So here you see that when I want to create this thing, so that is the we need to add support in this curves and other profiles shown here, so that by adding this, you see that approximately it takes around 2 hours 2 minutes to develop this product with the help of support by adding self-supporting ball. So here you see that this chamfers are given as a self-supporting things, so that we can able to reduce the production time. So around 1 hour 34 minutes it has been reduced due to this. So these things, you are self-supporting features you are adding through additive manufacturing only. Okay, sorry, in the design stage only. So all these things has to be done. So blindly we cannot do the design and go for all these steps involves the production time, material and other things. So how better you are using all this processes, so that I create a effective design. Okay. So then the third principle applied is the contour design. So here you see that what is the contours that are integrating. Okay, integrating the surfaces. So how the surface different types of contours, lattice structures or honeycomb structure, what how much pores we are leaving inside, how the load transfer is going to happening, what type of loading actually this is going to take. So everything by this design stage itself we have to calculate to decide upon the contour. Okay, so which will be helping you to decide on reducing the materials and then minimizing the production cost also, right? So the next one is how I'm going to segment it and bond the parts. So here you see that there are two 3D printed blocks, A, B, C, D. The images are given. So here you see that the blocks are of different segments and bonded together. So one first A section, you see that it is separated like a I section. Second one is a pi section, and then third one will be like a S section, and fourth one will be a V section where the interlocking has been provided. So by using this, so there the study conducted explains you that which interlocking requires or have a better strength during this compression testing. So they have suggested that it depends upon the what is the design that you are going to consider, and what type of profiles you are going to take, how much load is going to apply. So by S shape and V shapes provides a better integrity, so that these segments have a better strength while when they are assembled one to, right? Then addition of adwares, like addition of bushings where hot or abrasive materials will touch others. Okay, then you provide that tapping holes where you find this internal threads bolt or has to be fixed or screwed into the component. So this additive manufacturing, your design has to also include that, so that where it stops and how they are getting integrated into it. So this touch points or where you have to add magnet rods or fixture points, so that has to be decided uh, through this AM process. Okay, through this design process itself. Okay. So minimize complications. So here you see that unnecessarily don't add complicated shapes. Yeah, additive manufacturing is the process will help you in getting the product in the desired shape as you are thinking, but try to avoid unnecessary things. So here you see that both the A and B sides are shown. So in this B sides they have some special extruded things present in it. So if it is required, so see that the approximate time for creating it is was 8 hours, so that and the material volume also is shown. So whereas when you are reducing this, which has been almost 30 to 40% of the time has been reduced, so that you get a lesser volume of material in a reduced time. So these complications has to be avoided before you are going for the design. Um, uh, Avoided in the design stage before you are going for the process. Then we have this surface treatment. Say here there are two types of holes to be created. One is the horizontal hole and the other one is the vertical hole. Say the first thing that then you want to create the hole according to the requirement. If you try to create it through AM itself, it will be so this hole, when you try to make it with so the exact shape, building and other things will be costing you more material and time. So here you see you can able to create this diamond rings, so that you can dream it and then remove this, so that in the post processing operation, once the material has been processed. So similarly here this vertical holes, you see that they have given some l- purpose holes present inside the things where which is been reamed and been removed, so that the material is getting a good finish, and then the time is also reduced. So adding all this kind like additive thinking, design additive, providing orientation, proper orientations to the specimen, and then thinking about adding better bonding and strength. Okay, and then adding some better other components to during design stage. So all these things if you consider, so that you can able to create a better design for additive manufacturing before going for the process. So what workflow or the digital process or the chain that is being followed? So first is the conceptual design. So start by defining functional requirements. What we have seen so far, like you have to take into consideration the loading condition, whether it is a tensile load or a compressive load or a shear load, and what about the constraints where we are having the constraints and what type of applications is it. Considering all this, we use softwares like CATIA, SolidWorks, and then Onshape to develop a 3D model. So this is the most critical stage at which every futures affects the printability, support, need, and strength. So whatever we have listed in the previous slides has to be taken into consideration during this stage. So in the next stage, so the file will be exported, and then we are doing a validation to this. So export the models in a printable format such as STL or AMF models formats. So here you should ensure that there is a watertight, that is no open surface and no intersecting surface in the manifold, free of holes or mesh errors. So then you use tools like netfab or mesh mixers, so that which will be helping you to repair the STL files if you have any made any flaws during the design process. Okay. So the third process is the slicing and the tool path generation. So in which way our tool will be traveled so that the product is being created. So import the STL into slicer software such as Ultimaker Cura or Slicer or Simplify 3D. So here you see that the key settings which include in the slicing process is the layer height resolution. So the infill density and the pattern, that is whether it is a honeycomb or a grid or structures, and then the support structure where we required supports, and then the print orientation, which directions, and where I'm going to add layers which doesn't affect the surface finish and the strength of the product. So after which the output, that is the G codes, will be created, so that which guides the printer. Here you see that there are models and the 2D geometries and the tool paths are shown, how the tool will be traveling, so that which will be helping you to create. So you should be aware that so we I am using a optimized tool path. So the tool moves in a lesser, that is the tool path is very less in distance, so that I can able to generate the required product in a quicker amount of time. Okay. So the material and machine setup, so all might be other sessions might have covered regarding this. So choose the material based on the part performance and the printer type. So FDM, SLM, SLS and DMLS when you are using a metal laser sintering. Okay. So I'm not going deep into the materials. So after which the step what is the setup involves is loading the filament or the powder. After that, calibrating the print bed platform, verifying the nozzle or the laser alignments. All things has to be taken into considerations. Then the process flow, like printing and fabrication. So it depends on the process and the technology that you are going to use, where the printer will build up the layers one by one. After that, you will be getting the product which has been fabricated. So here you have to monitor the basic factors like printer addition, so better bonding of this, and the layer fusion and the stability of the temperature, right? So post which you will be doing the post processing operations, like any supports you have added, you will be removing the supports. So manual, water soluble or a breakaway supports, surface finish, so polishing or a vapor smoothing, and then heat treatment of for metal using additive manufacturing. So then the curing for the resin imprints. So finally you will be doing the inspection and the validation. So inspection, you use some CMM machines, calipers, so functional test, so revise the design based on the requirements. Okay, and then begin the iterative loop. So this is the design workflow and the digital process chain. So now we come into the functional design replacement, that is the industries, what they are doing or how they are using this additive manufacturing in a better way. So this plays a significant role in industrial practice, particularly in enabling the functional replacements of parts and components. So this technology offers a wide range of possibilities and advantages compared to traditional methods. So in the context of spare parts and legal components legacy component management. So here you see that there is a nozzle, 3D printed fuel inject nozzle, which was manufactured by Evenside and producing the first mass manufacturing site for aircraft engine parts using additive manufacturing. So what they did is, so the fuel nozzle was uh, generated them a larger revenue. How this is, they are providing better fuel efficiency than the previous generation engines, and they, because of the design what they have, design modifications what they bought. So in a conventional process they were difficult to create that design. So what happens, so that we have almost 18 or fuel 18 to 19 fuel nozzles, so depending upon the model of the engine. So these 3D printed models reduce the weight also, and provided good revenues to the companies by. So how this additive manufacturing in industry is helping a lot. Okay, so how they are giving is, they give the design freedom, so part consolidation, so better we go for multiple cards or a single requiring to the functional part, reducing assembly time and failure points. Okay, customization and mass customizations, so mass production also they are helping a lot. Rapid iteration and optimization, so you can able to change it very quickly and rapidly, so that you don't need to think about tool inventories and other things. Okay, so here you see that various industries and the functional part which has been manufactured with AI methods in aerospace, fuel nozzle brackets, where using this metal laser sintering, whereas in automotive we have fixtures, covers, holders, where you use FDM and SLS, railways, medical fields we use implants, bones, scaffolds, so SLA and SLS. So here we have this. Rolls-Royce company, so everyone will be knowing about it. So such a high-valued brand in cars. So they became a better beneficiary of this additive manufacturing components by getting a faster production. So you know that a very limited number of Rolls-Royce cars is being manufactured every year. So at there was an engine launch program. So where that Rolls-Royce company higher official has said that AM gives them a good opportunity. So because of conventional methods, they take around 60 weeks to manufacture an engine, while AM took only 1 month. So 4 weeks of time they raised that, and they have also saved 90% of the material to create the final component. So with the AM, that figure is much reduced. So that investing in AM will make them feel more confident, so that they have a better economic viability, and the process will be robust and reliable as a traditional methods, right? So now so these are being replacing in industries. So now our objective should not be only that replacement wind. So we also think about sustainable design practices and material efficiencies. So sustainable design prioritize or minimizing environmental impact and resource consumptions at every stage of a product life cycle, from material extraction and manufacturing to usage and end of life. So from which, so always you should be thinking about reduce, reuse and recycle. So designed to minimize material use, allow for reuse and facilitate recycling. So life cycle thinking, that is considering energy and resources, pollution and emission, waste generation, should be like this life cycle assessment with life cycle cost has to also to be considered. And circular economy principles, I think one separate topic is there in this FDP regarding circular economy. So that will be helping you to understand more about what materials to be used or reused for repurposed for extending the life cycle and reducing the wastage here. Okay, so here we use a material better efficiently, so that is achieving the same function with the lesser raw materials, that is lightweight. So by using better topology optimization, advanced modeling, so usage of this AI and MLs bringing into the design, so can be so that we minimal the loss strength or the utility, so that the components are having the same strength but with lesser weight. So durable designs, so how we are creating the parts so that it can be easily replaced, repairs, or upgraded so easily. And eco design, that is one of the factors that has environmental impact and support should be considered, so in all the industries. So here we have this best practices which are followed. So here you see that the additive manufacturing, ecological sustainability, and the design, so or more creating a eco design for additive manufacturing. Here you see that it is directly proportional to the maximization of the design benefits with the additive manufacturing and minimization of environmental impacts. So higher this minimization of environmental,
கலர் அதிகம் ஆனா
more will be. So the sustainable material selections, what is the preference for renewable and recycled materials, process optimization, and waste reductions.
பாடி தண்ணி தாங்கக்கா இருக்கா
So the industry drivers for sustainability in additive manufacturing. So you have environmental regulations, resource optimization, and industrial collaborations. So here you see that what are the environmental regulations which has been used for this sustainability in additive manufacturing. So the industries face increasing regulations and cutting greenhouse gas emissions, promoting circularity and ensuring transparencies. So through ESGs, environmental, social, and governance reporting. Um, Somebody has muted their.
கஸ்தூரி பேக்ஸ்குள்ள போனோம்
Sir, sir, are you there? Rajshekhar sir? Okay. So, what are the environmental regulations, resource optimizations, and the industry collaborations that have been happening in the recent times? Has been listed here. So, you see that the resource optimization, raw material saving, energy efficiency, and the waste reductions. So, what is this we are using? Like so here you see that additive manufacturing is a near net shape process which uses less primary materials and enables part to be manufactured very close to the final shape, which has been we have been seen in the first slide itself. So better having a better efficiency of using the energy and also having a less waste in terms of metal feedstocks and other things. So industry collaborators like majorly they are trying to use it in the aerospace where they required a lesser weight for their flying purpose. Constructions are working for research institutes and more startups has been built up to create this biodegradable and recyclable additive manufacturing materials to establish green standards in the supply chain. So the major industry roadmaps or step towards sustainability is transparency. So companies must track and openly disclose energy consumption, material inputs, waste for each manufacturer. This enables benchmarking, identifies areas of improvement in each processes. Life cycle assessment. So LCA, this is one of the important tool which will help in compare the environmental impact of additive manufacturers, those made conventionally methods one. So proper database and software will be used in this for predicting the life cycle analysis. Its prediction, okay, where we use AIs and new digital tools which has been developed in the recent times, so that it helps you to get better predictions, and then improvement with this all this green material recycling and energy reduction. So, what is the role of a mentor institutions or the skill development here? Why the government is more emphasizing in this? So here you see that they're trying to, sorry, so they are trying to government is trying to create a curriculum, so that they are updating the engineering colleges to add more curricula to teach towards additive manufacturing fundamentals alongside eco design, so life cycle thinking and circular economy, which is being emphasized by AICT or other board of studies in this individual universities, to bring it in the undergraduate curriculum, and then give some research leads to the students. So find some common labs in academic institutions by advancing the same recycling and using the design and other things, bringing the sustainability concept in the college stage itself. So upskilling the workforces, so training centers they are trying to make, and the government has also added this under industry 5.0, 5.0. So which is one of the important thing here. Additive manufacturing is taken into consideration. So they are funding collaborative project works, so creating knowledge hubs, and then they are making advisories, so which will they contribute more for the sustainability startups and established firms on implementing best practices for sustainable production. So sustainable additive manufacturing implementation. So major thing is material efficiency and energy efficiency. So which can be done through drastical reducing of scrap and waste materials in subtractive methods through additive manufacturing. So and then the energy manufacture. So here the sustainable design principles. So one is that the eco design additive manufacturing, incorporating this sustainable in this process to enhance recyclability. So nowadays you use this more of this polymers, we use biodegradable polymers, natural fibers to create this sustainable composites. So I think that is also one of the topic which is going to be covered in this session. I don't know whether it is completed or not, so it will be covered if not completed. So the life cycle extension, this, so how we are distributing and localizing the production. So manufacturing parts near the point of use drastically lowers transportation distance, cutting associated emissions. So more access to be created. So production on demand means where companies avoid overproduction, so in reducing inventories. So they provide a better approach, in particularly beneficial for customized small batch students and decentralized manufacturing. So the best practices here is conducting LCAs to quantify competitive environmental impacts and identify improvement areas. How I am going to improve it by identifying the life cycle assessments. So leveraging AI and digital twin technologies to optimize process, detect effects yearly, so that the model is the sustainable models, and bringing impacts in real time, collaborating across the supply chain, ensuring personnel are trained in circular economy. So nowadays you see that when you want to create some every institute, or there are not labs so everywhere where you create this product through additive manufacturing, you contact some suppliers, so they are reliable or comfortable with the 5 or 6 maximum materials, so that they in additive they through metal, if you take, they are comfortable with 2 3 materials like some alloys or titanium. Okay, so like that, so this has to be increased. So government is also planning to increase it, so trying to bring more materials into it. So some, but the challenges, they are facing more challenges. Certainly polymers are difficult to recycle, so they are working towards more recyclable polymers, balancing efficient process parameter with renewable energy, and then industry which currently lacks universally accepted sustainability benchmarks, so that has been coined and standards have been developed. So making consistent reporting and improvements is become difficult. So here we have a metal additive manufacturing life cycle analysis diagram. So here you see that this metal additive manufacturing life cycle diagram, the materials and the energy input data. Okay, so the extracted raw materials and powder which has been production uh, as given as an input in the raw material extraction stage, when they were move to design and manufacturing, so they are trying to develop some pollutants to the environments, and energy consumption is also happening. So after that, the distribution of that produced product, its usage and recyclable. So all these things should be in a circular process, such a way that the are getting recycled, so that the inputs like materials and energies are not wasted. So which has been measured by the atmospheric emissions, waterborne wastes, solid wastes, co-products and other releases which are trying to pollute the environments. So this has to be reduced. This we have to take into considerations by doing this. So the life cycle analysis has to be evaluated, so that this additive manufacturing process is a better efficient process, having both environmental and economic implications in this environment. So here you see that the technological futures of additive manufacturing are both having a positive as well as negative uh, impacts. So here you see that the environmental perspective enables the creation of lightweight designs and complex geometries. So here you see that the triangular thing. So towards sustainability goal, we have to consider this environment, society, and the economy. So what is the business ethics and a fair rate for the social responsibility, and how we are going to protect the environment and dredge natural resources. So in how we are going to get benefited by the government incentives and the taxes which promote efficiencies and better environment. So we have to concentrate on all these things to maintain a better sustain. So here there is a tabulated thing which measures the life cycle phase for design parameters. So like the design raw materials for life cycle phase, what are the design parameters? That is the height or product boundary dimensions. What is the electric energy consumption, ancillary resource consumption, material use, printing time in manufacturing. So the life cycle analysis and the cost also here has been showed, which has been involved in what process, shape complexity and weight, design raw materials and manufacturing, what are the transport use, part consolidations, the how we are going to design raw material, manufacture and transport it. So how I am going to consolidate it, assembly time and its complexities. So number of manufacturing process has to be reduced, so that the life cycle analysis is not affected, fuel energy consumption, easy dismantling, material recyclability. So and what type of material, what denser materials I have been using to design raw materials, manufacturing, transport and its use, material production. So how I am going to produce the material, raw material, manufacture it. Okay, then material recyclability. So here what kind of scrap it is going to create, how I am going to recycle the scrap, its toxicity of metal scraps. All these parameters has been measured for LCA and LCC analysis. Based on that, the metal additive life cycle assessment has been modified during the manufacturing process, how it has been automized and then transported in metal additive manufacturing technology, how we are reusing and redesign it, and then powder recycling, so that the process is being modified in this stage, right? So you have to think about this sustainable goal. So I use reused or recycled materials, so that we can able to move towards the government norms and create a better sustainability with a better economic and environmental concerns. So there are a few one case study which we are working here at NIT Agartala. So the we work under gears. So you see that gears are ideal components to demonstrate how this additive manufacturing design potential help you. So we have this per gears. So this 3D printer per gears, you can see that we are uh, this 3D printers per gears are having low load applications. So where the load applied will be less. So you can go for a metal additive, but due to cost effectiveness, we are not taking it. So we can able to create a custom module teeth count tailored to the application. So we can also integrate lubrication paths or mounting features directly into the gear body. So all of you know that gears, as we are from mechanical background, we know that how gears is being machined. So we required a cutter to be designed. So that cutter has to be designed so that the gear is being machined and then produced. So here you see there are different types of polymer gears shown. From the normal spur, red helical, and the bevel and the worm gears we have. So here you see when I'm trying to our research, we have worked in developing some modifications in the gear tooth profiles where we are trying to bring some non-standard tooth profiles so that we are trying to improve the load carrying capacity by creating different tooth profiles in the design stage. So creating this helped us achieve a better bending strength and contact strength in the design stage, which has been evaluated through some finite element analysis by creating some non-standard profiles or asymmetric spur gear profiles. Here you see that the course side and the drive sides are having different profiles in the asymmetric gear tooth, or we have this internal asymmetric gear tooth or non-cylindrical gears. So all these type of gears, so the manufacturing difficulties are there. Say I need to manufacture these things, I need to manufacture the tool, the cutter. So then I need to think about machining it. So proper things I have to do. But this AM helped us a lot in developing these things. So these additive manufacturing profiles are used in turbo propellers engines, which has been developed by Alexander and been used in the Russian aeroplanes. So here we have developed this metal asymmetric, polymer asymmetric, and then these gears. These are the image pictures of the SLS manufactured gear tooth surface. So along the uh, build-up directions has been shown here. So here you see that performing a crack study in a polymer gear, the images, micrographic images you shown here, how this type of pictures see that how the crack is being propagated into the tooth fillet. So in a polymer gear, this propagation is very predictable, whereas in additive manufactured gear, this is traveling in an unpredicted state. So there is a lot. We find that lots of research can be done in this particular area in which our team has been working on. So where we are studying this additive manufactured non-standard gears and non-circular gears. So by this 3D process, in which direction we are manufacturing it, so that we can able to check the crack flow. Similarly, we can able to check the bending strength, performance parameters of these gears, so that we can able to we are in the uh, plan of bringing the same strength as that of conventional gears has, with the help of this non-conventional designs. Here you see that the crack growth in it depends on the crack plane extended, how the layers is been constructed. So there are three ways of constructed layers. You can see how it is being propagated. So the propagation we need to arrest by converting this in this layers. You see, we can able to develop it in different layers, so that this propagation in additive manufacturing part uh, is getting influenced or significantly determines the failure life of the component. So the rate of crack propagation depends on the layer orientation. So which is in term determined by the build configurations. So there are different modes. So the cross laminar and the interlaminar things. So the interlaminar propagation, the crack propagates along the interface between consecutive layers. So whereas the laminar cross laminar mode, it absorbs high amount of energy, resulting in the retardation of the crack propagation. So which will be helping you to find a better material combination and a better layer build up, so that the metal doesn't fail due to this crack propagating, so that we can arrest it with the better combinations. Okay, so this is the area under which our team has been currently working. So I thanks the coordinator for this opportunity for giving me a session in this FDP. So I thank you all for listening patiently to my present session. So any questions you can ask, or we can interact regarding this. So whatever we have discussed for the last 1.5 hours. So thank you very much. Thank you for listening.
My sincere thanks to Dr. Ravi Varman sir for providing core concept of sustainable design for 3D printing and additive manufacturing with industrial standards and suitable case studies. Now the session is open to participants to clarify your doubts. Participants are requested to clarify your doubts with our expert.
So no questions. So So we are working in some collaborative works with IIT Guwahati also. So my contact details, mail ID, and my WhatsApp number is provided. So anybody interested to collaborate and work with this non-profiling gears, non-circular gears, or through AM methodologies, so you are welcome to contact me. So if there is no questions, I think can end the session.
Yes, sir. We can wind up the session 9, sir. Once
Okay.
again, I thank Dr. Ravi Varman sir for spending his valuable time with us. Thank you, sir.
Thank you, sir. Thank you very much.
Thank you. So participants requested to take 5 minutes break. Kindly assemble at 7:30 p.m. Kindly join the meeting at 7:30 p.m. Hello, Dr. Milan, sir.
Hello, sir.
Yes.
Hello, doctor.
Yes. Good evening.
Yeah,
Here
good
we have expert Dr. Milan D. Selvam for the session 10, Sustainability and Circular Economy in Additive Manufacturing. I am very happy to welcome Dr. Milan D. Selvam, sir. Dr. Milan holds bachelor's in mechanical engineering, master's in manufacturing engineering with PhD in mechanical engineering. Dr. Milan is a mechanical engineer, researcher, and academic leader with more than 15 years of teaching, research, and administrative experience across India and Uganda. He is presently serving as associate professor at Kampala International University, Western Campus, Uganda, where he manages research strategy, laboratory development, and academic mentoring. He is doing research in the field of sustainable manufacturing, green machining, and circular economic practices while simultaneously building institutional capacity and guiding young researchers. Dr. Milan has published 60 peer reviewed articles in reputed international journals indexed in Web of Science, along with 5 book chapters published by leading academic presses such as CRC, Taylor and Francis, and Springer. He has also guided 3 PhD scholars and many postgraduate students. Through his publications, patents, teaching, and mentorship, he supports globally sustainable goals with strengthening academic collaborations across borders. I welcome you, sir.
Thank you, Dr. Rajshekharan, and thank you for this opportunity. I thank the management, Department of Mechanical Engineering, for this opportunity to present a topic, sustainability and circular economy in additive manufacturing. So one of you, can you please confirm whether my voice is audible?
Yes, sir.
Okay. There is. Thank you so much. So there is a trouble I am facing here, and there is a serious weather problem. It is raining outside, and even some other event is going on simultaneously in my school. That's why. Is there any disturbances?
Slightly fast.
Okay, sorry for that. It is unavoidable. Thank you. So I will try to manage. I will try to see how I can present this topic uh, at most the level best. Right. So
Thank you,
shall
sir.
I allow me to share the screen?
Yes, sir.
Whether my screen is visible? Can anyone ensure?
Yes, sir. It is visible. Can
Okay.
you turn it on to full screen mode, sir?
Yeah, I have turned it on already. Is that okay? Is that moving?
Not moving, sir.
It's not moving. Let me, because of the weather condition, that's why I have shared, I have told you, the network is poor here. Let me turn off. Is that visible now, Dr. Rajshekharan?
Yes, sir. Visible.
Okay, all right.
Yes, yes. Now it is in full screen mode. Thank you.
Okay, so is that slide moving?
Moving, sir. Good.
Thank you. Thank you so much. So, good evening, members, learned professors, and participants of this faculty development program. Once again, I thank the management and personally to my friend, Dr. Rajshekharan, for this opportunity, and also to the Department of Mechanical Engineering I appreciate for conducting such type of events. Then let us go to today's business, that is sustainability and circular economy in additive manufacturing. That's a topic given to me.
Sir, can you can you
So
can you put down the presentation icon? Is there no in your presentation? Just drop down that one, sir. Yes, sir.
is that okay now?
Yes, sir. Thank you.
Okay, thank you so much. So let me come near to the mic so that the external disturbances may not disturb this presentation. So sustainability and circular economy in additive manufacturing, that is the topic we are going to see. So the limitation of this topic, I have presented some data also in this presentation, in this PPT. I haven't cited those data as you present like a research presentation. When you present a research, we usually cite that data. So I haven't cited that. So I have taken those data from generally available. So for an example, EU, that is European Union, that is a policy documents released by them, and also some regulatory bodies, documents from regulatory bodies, the common data. So those are the limitations of this presentation. Then that's we shall see here. We shall get into the business. Thank you. So why sustainability matters in manufacturing. So my presentation will be in sustainability. Then I will walk you through circular economy, then sustainability and circular economy in additive manufacturing, how it helps additive manufacturing, and how the whole the today's agenda helps in future research and even future policy adoption by the industries or even stakeholders. Right. So why sustainability matters in manufacturing today? Right. So there is two key terms like environmental impact and resource scarcity. Those are two tied terms, right? Two tied terms, right? And sustainability, right? Sustainability is maybe we can think the word sustainability attracts the publishers. We all are from academic field. We know publishing is also a criteria in academic arena. So sustainability for most of us, we may think sustainability as a fancy word, that if we use sustainability, right, sustainability in our papers or our research works or our publications, that will easily through into the editorial board, right? It will easily pass into the editorial board, right? It is not according to me, it is not just a fancy word to attract the researchers or academia. It has become, it is now a necessity, right? It is now a necessity. So manufacturing, right? So the manufacturing process, we all are mechanical engineers, I hope so. Most are mechanical engineers and engineering field, right? All the participants may be from engineering field. So manufacturing is an important aspect in the in mechanical field, right? So a data shows 20 percentage of the global GHG, that is greenhouse emissions gases, is from manufacturing. Others may contribute from the transportation sector and even domestic household, even commercial, etc., etc. But 20 percentage, right? Greenhouse gas emissions is from manufacturing sector. So if we continue, this 20 percentage is a significant value, very significant value, and it contributes a major percentage in greenhouse emissions. So if this business continue as usual, we will exhaust, right, natural, right, the natural well-being, and next, the resource scarcity. Resource scarcity. Next, the factor is resource scarcity. See, increasing scarcity of raw materials, right? Increasing scarcity of raw materials. For an example, for instance, we can look around in our, maybe those from villages. We may look around the natural resources. How our natural resources are protected. We are extracting all the natural resources. For an example, for construction materials, we are extracting sand, rocks, etc., etc. Likewise, in mechanical engineering expert, we are extracting all the metals, minerals from the earth. So if we continue such business also, we will exhaust, maybe in next 2 decades or the next 3 decades, we exhaust natural resources faster than we generate. That is a bitter fact we have to accept. One is environmental, one is resource scarcity. So manufacturers that embedded sustainability into operation are not only protecting the planet, our planet, but also safeguarding their bottom line, right? So when we speak of sustainability today, we are essentially speak about future proofing industry, right? So a business imperative says over 95% of world's largest company now integrate sustainability reporting, recognizing its direct link to competitiveness, profitability, and long-term viability in the conscious marketplace, right? So sustainability, right, is a multifaceted, right, and it is a need of the hour in engineering, especially in manufacturing, in all types of engineering. That is what we are going to see. Yeah. So what is additive manufacturing or 3D printing? I think this is the 5th day you all are attending the FDP, and many resource lecturers and has given enough input about additive manufacturing. I think I don't want to repeat the same, right? So it's a layer by layer digital design. Digital design can be printed into layer by layer, and any complicated or intricate shapes can be easily produced. So additive manufacturing, a game changer for sustainability, right? So there is a question, how it is a game changer. See, let us get clear about this AM, right? AM. So it is unlike about the subtractive manufacturing, that is a traditional manufacturing methods where we cut away the material, right? So cut away the material, and that is obviously a scrap or raw material, right? For an example, so why it is a game changer? For an example, a village, right? A village need to produce, right? For an example, in a village, a motor pump got a motor pump spare got some fault, and by that I mean that spare is unavailable there. By this method, we can reproduce that spare, right? That spare with less wastage or negligibly less wastage or even no wastage. That is the advantage of AM. That's why it is a game changer for sustainability. In case if we prefer some traditional manufacturing process, then just think about the wastage. For an example, a stat shows in machining, there is a quote called buy to fly ratio. So how much raw material you buy compared to how much actually flies, right? So it is colloquially buy to fly. In practically we can say buy and what is implemented, what is what we are getting finally, right? A stat shows that in machining, that is traditional subtractive manufacturing, the what we buy is, right, buy to fly is 5 to 1. There is a big loss in case of machining process, but it is also machining is also an inevitable manufacturing method, right? When compared to machining, this printing, the additive manufacturing, 3D printing gives very less negligible wastage, right? Wastage. So that is why it is a game changer, right? So the term wastage, it is directly linked to sustainability and circular economy. That is what we are going to see, right? There. So a scale a stat shows 2.1 billion tons of waste produced in European Union, right? European Union, highlighting the immense scale of materials discarded. So 2.1 billion tons of waste. It is a very big quantity. And then another linked to that, 190 kilogram of packaging waste per person per year in EU. That is also a significant contributor to overall waste streams, right? Then 14.9 tons of raw materials consumed per capita in Europe, European Union in 2022. That is another stat. See the current linear model. So linear model, I'm going to show you what is a linear model and what is a circular model. So current linear model, economic model, leads to unsustainable levels of waste generation and raw material consumption, right? So finite supplies and increasing import dependencies create significant economic and environmental vulnerabilities. That is the point, right? So that is what we have seen in the first slide, environmental vulnerabilities, right? And also economic for manufacturing sectors worldwide. So if we adopt circular economy, right? Circular economy, this wastage of 2.1 billion tons can be drastically reduced, right? Achieving zero, but it is impossible to achieve zero, but a considerable amount can be reduced, right? So what is circular economy? See, I want to explain this circular economy in simple terms. For an example, a forest where manual interventions are very less. The man interventions are very less. So a forest, A forest has trees, grasses, and even wildlife, right? That is different. See, a tree. A tree can be taken as an example. Tree in a forest can be taken as an example. So a tree, a seed is germinating into a plant, and that plant grows into a tree, getting the nutrition from the soil, right? And getting the the nutrition from the soil. So that nutrition, see, nutrition again, the leaves from the tree fall down, right? After they are aging, it will fall down, and it will decompose naturally, right? Become the nutrition, right? And this nutrition will supply us the food for those plants and those trees. This is what circular economy, in simple example, in simple language, this is what circular economy. There is no interventions of wastage, right? There is no wastage, right? That waste is also decomposing us and becoming a nutrition to that very plant, right? So linear economy and natural economy. See, linear economy leads to the step. So are we all together? Can anyone ensure? Hello? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you so much. Right. Linear economy. See, extraction of natural resources, right? Natural resources. And finally, after design, production, distribution, consumption, and disposal, it is going to waste, right? We have seen that 2.1 billion tons in EU. Just imagine about when that data is accounted for Asian continent, our own country, and even China. It's a highly populated countries as per stat, and even most of the Asian countries is leading in the population. Just I mean, assume the consumption of the product and even the disposal, final waste, right? So it is a big it is a big figure, right? Big figure of waste is annually produced. So what circular model or circular economy says is, so see, the same extraction of natural resources, obviously getting from natural resources, design and production, retail, consumption, collection, and finally no disposal, recycling, right? This is what the plant example I said, right? As a layman language, a plant example, this can, if this is introduced in additive manufacturing or any manufacturing process, so it can be said as circular manufacturing or circular economy in manufacturing engineering, right? So I hope it is clear. So aspect resource flow, you have seen the schema, that is illustration, the previous slide, the waste. So high often landfill or incinerated, right? So circular economy. So that waste disposal can be minimized near to zero, cannot be achieved zero, but near to zero. So materials kept in use that will reduce the raw material extraction. That's why it is said environmental, it is connected with environmentally and economically, right? Environmentally and economically. So product design, planned obsolescence common, and in circular economy designed for durability, repair, and recyclability. So environmental impact as well, right, as we discussed. So the key principles of CE, that is circular economy, are keep products and materials in use, regenerate natural systems, right? So design out waste and pollution, promote the system, right? And widen the innovation. So there is a wide scope for research. Those for researchers, there is a wide scope in circular economy. Then design for recyclability and reusability, right? So, example, modular electronics, right? Modular electronics. So, consider modular electronics where components can be individually upgraded or replaced rather than requiring them the disposal of the entire device when one part fails or becomes outdated. This approach is transformative for the product. See, I don't know how fact it is, right? How fact and how far we are using that, because practically speaking, we have to see the software and even the versions of even the electronic goods, whatever we are using now, what are the smartphones, the computers, and so and so. Right, that is a different matter. So what it says, the schema says is this electronics can be replaced by any other terms, automotive products, or even the synthetic oil used in manufacturing, right? Synthetic oil used in manufacturing, right? So this is what a closed loop system recyclability, that promote the recyclability and reusability, right? Reusability. So in the closed loop production and recycling, there will be a provision for material recovery, right? And in additive manufacturing, recycling the metal powders, right? Metal powders. So closed loop productions are essential to the CE, where materials are continuously recovered and reused within the manufacturing cycle, ensuring minimization of waste and maximizing the resource efficiency. Then sustainable consumption and production, right? Sustainable consumption, that is what we were discussing. What I will say is responsible consumption also. Along with sustainable consumption, it should be responsible consumption and handling the waste, right? Handling the waste. Okay, maybe we shall discuss in a case study. So circular economy benefits for manufacturing. It's supply chain resilience, economic growth, as well as jobs in especially in the recycling processes. Then emission reduction to save the environmental impacts. Then innovation catalyst. So innovation. So we engineers, we are tasked, or we are intended to for innovation and research and innovation, obviously. So if there is a no innovation and research, obviously the country will face serious trouble even after 5 years, or even a decade, in 10 years, right? So there is a bigger chance in of innovation and research in circular economy. So coming to the topic, how AM, that is additive manufacturing, supports circular economy in manufacturing. Repair and refurbishment. So AM enables the rapid production of custom spare parts, extending the lifespan of the products by making repairs more feasible and cost effective, right? You are learning about AM. Okay, hope that is well understood. So, sustainable feedstocks, right? So, there is a growing trend for additive manufacturing to utilize. Uh, Dr. Rajshekharan, hello.
Yes, sir. Yes.
So, can you advise someone that is to mute their
Yes,
mic?
sir. Yes, sir. Yes, sir. I have done it.
Thank you so much.
Now you can continue.
Right. There is a growing trend for additive manufacturing to utilize recycled or bio-based materials as feedstocks. That is a key point. Bio-based material. So bio-based material is another aspect of sustainability, right? Sustainability as it naturally decompose and never harm the what environment. And so this reduces reliance on the virgin raw material extracted and closes material loops, lessening environmental impact. That is a greater example for now for this sustainable feedstock. So biodegradable electronic materials. So electronic materials is creating a bigger attention nowadays. So biodegradable electronic materials. So you can search in databases, research databases for recent research on that. For those for budding researchers. So design for circularity, another aspect in AM. So AM allows designers to create products with disassembly and recyclability in mind from the outset. This design for X, so and so X approach is crucial for facilitating future material recovery and reuse. So some real world CE, that is circular economy in action, right? So that is okay. That is a general aspect. Let us go to the business. Some example, in the interest of time. So the path forward for manufacturing, right? Sustainable manufacturing, essential, imperative. So embracing the sustainability and CE principles is no longer optional, right? It is not an option. It is a need for now. And AM as an enabler. So AM stands out as a powerful enabler of circular strategies, driving innovation, enhancing resource efficiency, and facilitating new models. That's what we have seen, right? So transformative potential, right? So the time is to act is now. We must collectively design, produce, and consume with circularity at the core to secure, right? Yeah, sustainable future. So circular economy principles, redefining sustainable manufacturing. Right. Thank you. So benefits of CE in additive manufacturing, right? Another aspect, another two aspects: material savings, economic opportunity. That is okay. That is okay. So we have discussed that. Another aspect, life cycle extension, right? Life cycle extension. So that additive manufacturing has a capability that it is efficient for what to produce complex parts significantly. It can prolong, right, the usage and reduce premature disposals. Then next aspect is the supply chain. So localized production capabilities afforded by AM can reduce dependency on fragile global logistics and extensive inventories. right? Building more robust supply chains. Then a case, right? A circular economy in additive manufacturing. Circular economy in additive manufacturing. See, Italian startup called F3 Nice, right? F3 Nice is a startup. It's a company started in 2020. If I am not wrong, it is 2020. It is a pioneering example of circular economy principles applied directly to additive manufacturing, especially. So they specialize in producing high quality additive manufacturing metal powders, but with the critical difference. Their powders are derived from 100% recycled scrap metal. That's how they claim, right? So it is a very big initiative. The startup has recently initiated. So it is an Italian company. So the company has successfully raised $120,000 in pre-seed funding, demonstrating investor confidence in their sustainability. It's not a small money; it's a very big money. $120,000 is some crores in Indian rupees, right? It is more than it seems it's near to a crore, 1 crore of rupees. It's a big fund raised that demonstrate the investors are confidence in sustainable approach and potential for scalability in this green powder production. So this company utilizes a patent pending process that transforms what would otherwise be industrial waste, such as decommissioned valves and absolute those outdated metal parts into creating it into a valuable high grade powder feedstock for 3D printing. It's a great initiative. And this innovative approach fundamentally disturbs the traditional raw material mining and processing, proving that circular principles are not just environmentally responsible, but also commercially it is viable. They have proved it is commercially viable and technologically advanced. Then the challenges and opportunities in circular economy for especially in AM. So the challenges is always in any process, any advancements there will be challenges, and challenges obviously it is a pathway to future research. So first one is new feedstock development, right? So the need for a wider range of recycled feedstock materials that are compatible with the various additive manufacturing processes and meet stringent quality requirements. That is considered as the first challenge, and the product and supply chain redesign, right? So significant investment and innovations are required to redesign products and entire supply chains to fully embrace circularity, often involving new partnerships. Then scaling recycling technologies, developing and scaling efficient, right? Cost-effective recycling technologies for additive manufacturing materials while ensuring consistent material quality to meet demanding specifications, right? Then opportunities. Another key important area for the budding researchers is a life cycle assessment in integration. So implementing LCA is a key area and a hot area now in manufacturing engineering research. So implementing LCA to quantify the environmental and economic benefits of circularity, providing data-driven insights for improvement. Then cross-industry collaboration, promoting partnerships across sectors to develop industry-wide standards. Then digital design and optimization. So leveraging advances in digital design tools and topological optimization to maximize resource efficiency and integrate circular principles from the consumption. Right.
எனக்கு பூ பைத்தியம்லாம் கிடையாது. பார்த்தா
நிறைய இது இருந்தாலும் அடுத்தவங்களுக்கு கொடுக்கணும்.
Thank you. So future directions we shall see in the next slide and the next coming slides. So sustainability in additive manufacturing. Then the environmental footprint of traditional manufacturing. Right, traditional subtractive manufacturing. So see, before dividing it into the sustainable potential of AM, it is crucial to understand the challenges posed by conventional methods. So the traditional methods possess often involve significant material wastage, right? High energy consumption process and complex supply chains. So all of which contributed to a what substantial significant environmental impact. Then benefits of AM for sustainability, right? So this we have seen already. I'm skipping this slide. Then sustainable materials, very important. Sustainable materials in AM. So this you can directly link to the circular model or a circular economy or a closed loop production process. See, the choice of materials is crucial for the overall sustainability of additive manufacturing. Innovations in this area is rapidly expanding the range of eco-friendly options from recycled plastics and metals to novel bio composites, right? So a better example I mentioned is a biodegradable electronic materials. So sustainable plastic materials or sustainable materials is used in electronic materials in order to replace the existing non-biodegradable materials or non-sustainable materials, which supports the circular economy or circular model. So see, the products, the materials are recycled polymers, utilizing post-customer and post-industrial plastic waste as feedstock for FDM and SLS processes. Those are AM processes, you know well. Diverting waste from landfills. That is important. That is how it supports the environmental disaster. Bio-based materials, development of biodegradable and compostable filaments derived from renewable resources like cornstarch, right? That is PLA or lignin. Those polylactic acid, that is a recyclable bio-based material which is also used in biodegradable electronic materials, PLA, lignin, and so many, right? And so many. Recyclable metal powders, growing adoption of metal powders that can be recovered, reprocessed, and reused in powder bed fusion processes, minimizing the virgin material demand, that is the raw material extraction, right? So this is always the sustainable materials is always a hot research area that gives various gaps for future research. So the energy efficiency in AM. So how AM supports the energy efficiency? See, while some AM processes, particularly those involving high power lasers or electron beams have high instantaneous energy demands. The overall energy footprint often compares
பாதி இங்க
favorably to the
மறுபடியும்
uh,
ஞாயிற்றுக்கிழமை வந்தவங்க போன பண்ணி கேட்டா சொல்லிட்டாங்க
favorably to the traditional methods. Can you please turn off your mic?
நல்லா பேசுவோம் நல்லா சிரிப்போம் அடுத்த நாள் ஆப்போசிட்ல வரும்போது
Dr. Rashegran?
பேசினாலும் பேசுவாங்க
Hello?
பேசும்போது நல்லா பேசுவாங்க
Are we all together? Okay, thank you. So, optimized designs. So, AM enables lightweighting and design optimization, leading to less material usage and consequently reduced energy in material production. Then on-demand production AM eliminates the need for large inventories and associated energy for storage, heating and cooling, and localized production. It AM reduces energy consumption related to transportation across complex global supply chains. So efforts are underway to integrate renewable energy sources into AM facilities and to develop more energy efficient AM machines, further improving their sustainability profile. So, reduced material waste in AM. So, how presented a data 90% less scrap, right? As I said, towards that is reaching zero wastage, right? That is how AM supports circular model. Some AM process can reduce material waste up to 90% compared to conventional machining. Then near net shape, minimal post-processing. AM parts often require less post-processing. Example, machining, finishing, further reducing material loss and energy use. Dear members, I sincerely apologize for the noise. It is unavoidable. Please excuse me, please. So I hope it is disturbing as well. So powder reuse. So recyclable powders in the processes like SLS and powder bed fusion, unused powder can be collected and reused, approaching a zero waste system for materials. Right. Then increased product complexity and customization, like lightweighting, consolidation, and improved performance and lifespan. So reduced transportation and storage needs. That's digital inventory. Instead of physical stock files, designs can be stored digitally, produced locally when needed, minimizing warehouse space. Right? Members, please excuse me for a minute, for a while. Sorry, some events going on. That's why this disturbance. Sorry for that again. Right. So, how sustainable additive manufacturing supports in aerospace industry? See, so see a GE Aviation fuel nozzles is a case study. So GE Aviation now 3D prints fuel nozzles for its LEAP jet engines. This consolidates 20 separate parts into a single more durable component. See, the advantages: reduced weight, right? The AM nozzle is 25% lighter than the assembled counterparts. Then improved efficiency, enhanced design leads to better fuel atomization and engine performance. Then material saving, that is the major matter. Material saving, the near net shape production significantly reduces material waste. Then the impact is even a small weight reduction in aircraft parts translate to substantial fuel savings over the lifespan. You know, we all know well, fuel is a natural resource and extracted uh, as a natural resource, a mineral, right? Obviously it is a raw material extraction. Petroleum is a raw material extraction, and continuously if we extract once in a while, there won't be any fossil fuels. There should be some alternate to be found. The major matter is fuel efficiency. Fuel efficiency can be also achieved in case of AM manufacturing. That's what the case what lessons us. Okay, so challenges and future directions in the aspect of the connected to the case studies. Let us skip this slide because we have seen this in the previous. Right. Likewise, in aerospace, the transportation sector, that is automotive in manufacturing, right, also beneficial with this additive manufacturing, with so many advantages like um, reduction of material waste, reduction of high energy consumption, obviously fuel efficiency by reducing the pollution emissions, and okay, etc. Let me also skip this slide since we have seen. Right. Lightweighting automotive component, as I said. So the stages in AM process. So initial design and analysis, right? Engineers redesign the bracket. So a bracket as an example using the topology optimization software, identifying areas where material could be removed without compromising structural integrity. That is a factor, structural integrity. Then the proper material selection. So how material is selected, and so the recycled aluminum powder, alloy powder, so suitable for PBF process, ensuring both strength and circularity. Then the third stage is 3D printing. It's the AM process, and the final stage, the post-processing and validation. Minimal post-processing was required. The common underwent rigorous testing to ensure it met all the performance and safety standards. Right. So a additively manufactured bracket for automotive application. So tangible results from sustainable additive manufacturing bracket case study, the previous one. So 35% weight reduction, 20% material waste reduction, and 15% energy savings, and 10% reduced assembly time. It takes us to the circularity or circular manufacturing model or near what you can say what towards sustainable engineering a model. So beyond the bracket, the broad impact of sustainable additive manufacturing. So this is also a repetition of whatever we have discussed. I don't want to repeat the same. Let me skip that. So the challenges and path forward. And the benefits of sustainable additive manufacturing are compelling. It's a widespread adoption in that's automotive sector, faces certain challenges like scalability and speed, quality assurance, then cost of materials and equipment, then skill gap, right? A shortage of engineers and technicians skilled in AM design, operation, and processing needs to be addressed. So that is a gap denoted for us for our future considerations to be skilled and research in that area. Then the future of SAM, that is sustainable manufacturing, automotive manufacturing, integrated green energy, right? Then bio-inspired design. So the leveraging the bio mimicry. So that is another research area for the budding researchers to create ultra lightweight and high performance parts with the minimal material wastage. Usage, then advanced recycled materials, then decentralized production, then obviously the AI driven optimization, artificial intelligence integration, right? So challenges and opportunities, maybe we shall see as a summary. So technical challenges. See, the journey of circular additive manufacturing faces significant technical roadblocks. There where we stand as engineers, we need to address or we need to work on that area, technical roadblocks, right? For the future manufacturing sectors. Then one primary concern is the development of repurposable and recyclable materials that to maintain high performance, right? So the material have to give what the performance as well, high performance as well, and the current feedstock often lacks the durability and reusability required for closed loop systems, leading to downcycling or wastage. Then, moreover, process efficiency and energy consumption remain critical areas. So many AM processes are energy intensive, and optimizing them for sustainability without compromising part quality is a complex engineering challenge. This includes reducing support material waste and improving post-processing techniques. So, a pathway to overcome those technical hurdles is advanced material science, right? That is developing new polymers, the new materials, metals, and composites that are inherently recyclable or biodegradable without sacrificing the key term, the mechanical properties, printability that will give what the that is targeted to give the high performance. Focus should be on bio-based and waste-derived feedstocks. That is how our topic, circular economy, comes in. Focus on bio-based and that is recycle. combustible, naturally decomposable materials, and process optimization. So innovating in the machine, right? Innovation in the machine to reduce energy usage, minimize the material waste, and enhance reusability, and design for circularity, promoting design methodologies that facilitate easy disassembly, repair, and recycling 3D printed components, and economic challenges as well, right? Let me take you to the data. So 40 percentage key economic drivers and benefits. See, 40 percentage material cost reduction, potential savings from using recycled feedstocks and minimizing waste during production, and 25 percentage logistic efficiency, decreased transportation cost and lead times through localized and on-demand manufacturing. This can be increased in a period of time. Maybe in the next 1 decade, this data may even increase due to the interest in sustainability among the entrepreneurs, that is the investors. And 15 percentage of market differentiation, gaining a competitive edge by appealing to environmentally conscious consumers and corporate partners. Then regulatory challenges and opportunities, material certification, then waste management and product liability. So lack of standardized certification process for recycled or bio-based AM materials. So obviously, when we talk about future sustainability research, and there should be policy implication as well. We have to consider that also in mind. So then waste management, ambiguity in regulations regarding the classification and disposal of AM processes by products and end of life parts. Then product liability, determining liability for products made from recycled materials or designed for multiple life cycles. Then social and environmental impact. Then so environmental benefits that we were discussing. We have discussed. Thank you. So the social benefits is job creation, new roles in material recovery, recycling, and advanced manufacturing. Then localized production, boosting local economies and promoting community resilience. Then ethical sourcing, right? So greater control over the origin and impact of materials. Then why sustainability matters now. That is how we are now in the consolidating the lecture, concluding the lecture, whatever we have gone through, right? So we have started our lecture from need for sustainability, and now it is why sustainability matters. Accelerating resource depletion. See, global resource extraction and waste continue to accelerate and threaten our planet where we live. So as highlighted by a researcher, so our consumption patterns are depleting natural capital at an alarming rate, jeopardizing the future generations, right? So resource depletion is a major concern, and environmental cost, mounting the environmental. So food waste alone, right, accounts 8% of global GHG. Another what GHG contributor, as manufacturing contribute 20%. we face this. See, resource depletion and environmental, that is linked. So then unsustainable linear economy model. So linear economy model, that is the existing take, make, waste. That is take, make, consume, dispose. Consume, dispose, that is waste. Obviously waste, that's a linear model, which is fundamentally, and it is highly unsustainable and costly for both the environment and the businesses. It relies on endless growth and finite resources, a model that cannot persist indefinitely. And the barriers and how we overcome them. See, the overcoming challenges in circularity. The path to a fully circular economy faces obstacles, but strategic interventions and collaborations, that is what needed. Collaborations can overcome them. It requires a concerted effort from all stakeholders. Then a lack of consumer awareness and inconsistent government policies. That's what we discussed. So whatever there will be research, there should be proper government policies and regulations. So for proper implementation. So see, the lack of consumer awareness and inconsistent government policies. This inconsistent government policies is universal. It's applicable to any country. Currently, slow down the progress, as highlighted by Ivy Business School. And education and clear policy frameworks are essential, which is a clear benchmark for our for me and you as we are in teaching. So overcoming these barriers requires strong collaboration across sectors, widespread education, and implementation of supportive regulation that incentivize circular practices, then successful public-private partnerships, and also I also propose industry academia partnership. That is also essential. Industry academia partnership and innovative circular procurement initiatives demonstrate that these challenges can be effectively addressed with commitment and strategic planning. So how we can make a difference, right? So I mentioned as we can make a difference. So conscious consumption, that is the main for implementing circular economy. Then support circular businesses and reduce personal wastes. That is obviously linked with conscious consumption. So consciously, if we consume, there won't be much waste. So choosing a product designed for longevity and repairability and recyclability, and prioritizing items that last and can re-enter the material stream. That is consciously consuming. Then supporting circular business model that support businesses genuinely committed to circular practices and have robust sustainability goals, right? So those 17 goals, SDGs, right? Empowering those leading to the transition. Then reduce unnecessary waste throughout reusing, repairing, and recycling. Minimizes as well the environmental footprint in daily life. So collective impact and collectively together. There is a quote called "Together we win." Together we can educate. Together we can bring some changes, right? So the transition to circular economy is gaining global momentum, driven by governments, organizations, and individuals. So governments worldwide, including Some of the countries I have captured, maybe even many, right? That's why in the beginning of the presentation I said I have presented some data that haven't cited well. This is not a regular research presentation, but it is a general, maybe a knowledge sharing or a general lecture, right? So Canada and European Union, not all the countries in European Union, most of the countries are implementing comprehensive CE strategies to build resilient. Then for also local carbon economies, integrating circularity into national policies. Then organizations like the Circular Innovation Council offer invaluable opportunities to collaborate and innovate, uh, promote a community dedicated to advance circular solution and share best practices. Then finally, together we possess the collective power to redefine value, protect our planet, and ensure a sustainable future for generations to come. Every action, big or small, contributes to this vital movement. And future research directions that we are seeing throughout this presentation. So novel material development, then enhanced recycling infrastructure, then integrated process design, and the key element I said, life cycle assessment tools. Then key takeaways and the next step is a sustainable AM is inevitable. Then collaboration is crucial. So investment in research and development, right? The knowledge investment for us, it is a knowledge investment. So next steps are form cross-sectional teams, collaborations, pilot circular initiatives, start a small-scale projects to test recycled materials and closed-loop processes. So advocate for policy, engage with the regulatory bodies to shape supportive frameworks. So educate and train, right? Develop programs to upskill the workforce in sustainable AM practices. So together, let's build a circular future, one layer at a time. So time to act is now. Sustainability and circular economy are not just ideals, they are essential for our collective survival and prosperity, right? So let's commit today to think circular, act sustainably, and inspire change in our communities. And thank you all. If there is any queries and questions, you can ask. We shall discuss as much as I support. So again, I apologize for the external disturbances, and I don't know whether there is any network disruption from my side. But I know there is external what noises. That's I said there is a event going on parallelly in my school, in my department. Okay, so thank you so much, members. Thank you for this opportunity. So now the session Q&A, sir.
I thank Dr. Milan sir for providing core concept of circular economy with detailed case studies on additive manufacturing. Thank you, sir. Now the session is open to participants to clarify your doubts. Participants, you can clarify your doubts. I have posted link for the feedback for the day 5 feedback?
I think in the absence of any, I will share the copy of this PPT to Dr. Rashegran, and maybe you can collect those copy from Dr. Rashegran. So you can, if there is any collaborative needs, you can contact me as well. My contacts are also there in that PPT. So, sir, what is next?
Sir, if there is no clarifications from participant side, we can wind up the session, sir.
Thank you. Thank you so much.
Yes.
Thank you once again for this opportunity. I thank the management.
There is one question, I think, from Mahinder.
Yes.
Sir, it is posted in the chat box. Can you see the chat box, sir?
Yeah, let me open.
One.
Sure. Uh-huh. How does AM, that is additive manufacturing, help in reducing material waste? So, sir, yeah, let me consider this as a general question. Even I have given a comment. See, yeah, near net shape. There is a terminology called near net shape. So that near net shape supports in reducing the the product developed, right? Product developed without further assembling process, or even further wastage. See, when compared to subtractive manufacturing, subtractive manufacturing, for an example, machining, we remove material in order to bring it to a shape. In case of AM, we print, we design it and print it, right? Layer by layer, we print it to bring the final shape. Okay, that even what is a best example for the material reduction, material wastage reduction example. That's how AM supports circular economy and sustainability. Is that clear, sir? Dr. Mahendra. Okay. So if there is any, thank you. Okay. If there is
Yes,
any,
respond.
okay.
Any other classifications from
Any
participant
more
side?
queries you can post. There is another, please suggest sustainable material for FDM process, and what is the life of product which is made of AM. And see, in my presentation, two more questions. In my presentation, I have suggested some materials, and even life of a product, life cycle assessment. The second question is life cycle assessment. It is always the what? The raw material, that is material for AM processes, and life cycle is always a research area. It is always a research area, and obviously you can scholarly publications, right, for recent researchers and recent materials in that. Anyhow, I will share the my presentation as well, right? It has a general overview on life cycle assessment and even the materials. You go through that, more you can read from scholarly publications.
Any other clarifications from participant side?
Uh, Thank you. In the absence of any, I think I thank the participants as well for joining this session. Thank you so much once again.
Thank you, sir. So we can, participants, we can wind up the session 10. Session 11 will be started tomorrow at afternoon 2 p.m. Thank you all.